Hello students, so we have started with the series practice with me. Okay, so we were doing derivatives, some problems, okay, practice problems. You can practice these problems and write on your notebook. Okay, so we'll do the next question. So the question is, if e raised to x plus e raised to y is equal to e raised to x plus y, okay, then you have to prove that dy by dx, that is its derivative, is e raised to x e raised to y minus 1 upon e raised to y e raised to x minus 1. Okay, this we have to prove. Now starting with what is given, okay, e raised to x plus e raised to y, take the derivative of this function. So e raised to x derivative, this is again implicit function. Okay, so e raised to x derivative is e raised to x, e raised to y derivative is e raised to y, and then derivative of y, that is dy by dx. Then you have to derivate this e raised to x plus y, composite function. So you have to then write the derivative of this function x plus y, that is 1 plus dy by dx. Now we want dy by dx, right? So we have to take together the terms with dy by dx. So this you can write and take inside e raised to x plus y into 1 plus e raised to x plus y into dy by dx. Okay, now take the dy by dx terms together. So this is e raised to y, and if we take this term this side, then it will be minus e raised to x plus y dy by dx equal to e raised to x plus y, and this term I'm taking this side, so minus e raised to x. Okay, so dy by dx is e raised to x plus y minus e raised to x upon e raised to y minus e raised to x plus y. Okay, now you can take e raised to x common, because you can write this as e raised to x into e raised to y, right? And this is as e raised to x into e raised to y. So taking e raised to x common, you will get here e raised to y minus 1, and here you will get 1 minus e raised to x. Right? Okay, here it was minus sign, so in the question, so you can write this as e raised to x minus 1, so you can take out the minus sign. Okay, here in the question it was minus here. Okay, so this is the answer. In next question, you have to find dy by dx when this is given, log of x plus y equal to 1. Now this is again implicit function, that is y is there in between this, so I'll take this as u, this as v. So uv, derivative of uv function you have to do. So first I'll keep u as it is. Derivative of this is 1 upon x plus y, and derivative of x plus y, that is 1 plus derivative of y is dy by dx. Okay, then you have to write plus derivative of xy, that is Again here UV rule will apply, that is x is u, y is v. Okay, derivative of x is 1 into y plus derivative of y, that is dy by dx. Okay, and log of x plus y remains as it is. And the other side here it is 1, right? So derivative of 1 is 0. Okay, now you have to arrange the terms so that you get dy by dx. So this is xy upon x plus y 1 plus dy by dx plus, I'll take that log here, log inside this, so this will be y log x plus y plus x log x plus y dy by dx equal to 0. Okay, again taking 1 inside means multiplying this inside, you will get dy by dx term. So this is one dy by dx term and that one, so I'll write them together. Okay, now I'll take this whole term that side, so this will become minus and minus. Okay, now I have to write this term here, that is divide by, so divide by okay, so this is our dy by dx, this term. Okay, next question. So you have to differentiate, that is y equal to e raised to x log of root of x and tan of x. Okay, so these are functions which are multiplied, so chain rule you have to use. Okay, this is function 1, function 2 and function 3. Here you can use property of log, that is log of x raised to half, right? So this is log a raised to b, which we can write b log a. Okay, so here you can write half, this goes, and you can derivate this function, so dy by dx, so this has become your u, v and w. So when you are derivating u, you have to write v and w as it is. So this is e raised to x, derivative is e raised to x, both these functions will come as it is, plus e raised to x remain as it is, then log of x derivative is 1 by x plus last one tan of x derivative is x square x. So this is the derivative. Okay, next one. So derivative of this is composite function, log function is there and inside it there is one more function. Okay, so dy by dx derivative of log 1 by that function which is given. Then we have to write derivative of this function, x is 1, derivative of root function, that is 1 upon 2 root of x square plus 1, and then derivative of the function which is inside x square plus 1, which is our 2x. Okay, so this becomes, if you take this inside, this will be 1 upon x plus root x square plus 1 plus 2x upon x plus root x square plus 1 into 2 root x square plus 1. 2 goes. Okay. If you want, you can multiply this inside or write this as it is. Okay. Next question. So whenever you get this type of functions, okay, sine inverse something or tan inverse something, go for its trigonometric values. Now we have sine to theta and cos to theta, right? First we'll write this as sine inverse 2 raised to x plus 1 can be written as 2 raised to x into 2, right? And 4 raised to x means 2 raised to 2. 2 square raised to x. So I can write this as x raised to 2. So that this two becomes equal. Now we can make use of sine to theta formula, that is in terms of tan. So we can substitute here 2 raised to x as tan theta. Okay. So derivative, so theta will be what? Tan inverse of, we are taking this as 2 raised to x. Okay. So if you put this in y becomes sine inverse 2 raised to x is, so 2 tan theta upon 1 plus tan square theta, which is nothing but our sine 2 theta. Okay, so using the inverse trigonometric functions, this becomes 2 theta. So y is 2 theta, and we know the value of theta, that is tan inverse 2 raised to x. Okay, now you have to derive it. So dy by dx tan inverse of 2 raised to x, tan inverse of x derivative is 1 upon 1 plus x square. So 1 upon 1 plus 2 raised to x square, and then derivative of 2 raised to x, which is 2 raised to x log of 2. Okay, so this will be 4 into 2 raised to x, not 4, it's 2 into 2 raised to x log of 2 upon 1 plus 2 raised to x square. This is your dy by dx. Okay.